LU decomposition, just two words and there's so much confusion here. For most people who just start learning linear algebra, that might sound like an abracadabra. But please don't avoid this topic because you think this is difficult, because it is not. So what is the LU decomposition and what does that mean? Watch this video until the end, because in this video I'm going to provide clear explanation of what the LU decomposition is, along with the practical examples and the algorithm behind that. So LU decomposition is just when you split your matrix into two parts, the lower triangular matrix and the upper triangular matrix. By the way, this is not always possible, and in this case we use different decompositions, but don't bother about this too much. We're gonna consider a simpler case today when LU decomposition is possible. So if you're watching this video, you're probably someone who encountered the LU decomposition before and just wants to know what it actually means. Or here's someone who hears about this for the first time and wants to know what this thing is all about. So I already mentioned that LU decomposition is like splitting your matrix into two parts, the lower triangular matrix and the upper triangular matrix. But what is the whole point behind this process? And this is simple. It turns out that everything just comes down to solving the systems of linear equations. You know that the system of linear equations is just like having many linear equations bundled together. And when we need to solve them, we basically need to find such all values of variables when all these linear equations hold, right? So to put it shortly, LU decomposition is a pretty cool technique of solving these systems efficiently. But let me just digress for a moment. As you know, mathematics gives us many different ways of solving systems of linear equations. And one such technique is Gaussian elimination, by far one of the most elegant ways of solving systems of linear equations so far, especially when you're doing this by hand. And you may ask a very reasonable question here: why can't we just apply the Gaussian elimination every single time when you need to solve systems of linear equations, especially when it sounds and looks so simple and straightforward? What is so special about breaking the matrix down into its components like lower and upper triangular matrices? When should we actually prefer the LU decomposition in the first place? I'm going to answer this question pretty soon, but let me first focus on giving you a simple example of what the LU decomposition is so you get the intuition behind this. Alrighty, so here's the matrix A. 2, 3, 4, 7, 4 elements in this matrix. So this is the matrix of size 2 by 2. So how can we find the LU decomposition of this matrix? In fact, that's pretty simple. All we need to do is to make this matrix look like upper triangular matrix first. And then we need to keep track of all operations that we applied on this matrix to make it look like upper triangular. Let me show you what I mean by this. So first of all, we're going to make this look like a upper triangular matrix. We just need to apply elementary operations here. We take the first row, multiply it by -2, and then apply this row to the second row, and we're going to end up having 2, 3, and 0, 1. That's very simple, right? That's just one elementary operation. And we keep track of this. For this purpose, we have another matrix, which is called lower triangular matrix, and this lower triangular matrix also consists of ones on the main diagonal. So it consists of ones on the main diagonal, and then the elements below this main diagonal is basically those multipliers that you used in your elementary operations to obtain your upper triangular matrix. So you basically used -2 multiplier to apply the first row to the second row, right, and get 0. So you need to keep track of that. And you don't just write down the -2 here. This is not -2. You need to take the negative of that multiplier. You use the +2. So you have to use the +2 here. So this is the lower triangular matrix. It looks very simple because, well, this example is pretty simple. And you can make sure this works. You can make sure that LU is actually, this is U, right, is exactly A. So we can make sure this works. How can we do that? So we just need to multiply these matrices. And let me demonstrate this for you. You have 1, 0, 2, 1 times 3, 2, 2, 3, sorry, 0, 1. So you're going to end up with 2, 3. This is the same. And then 4, and then 6 plus 1, which is the 7. This is the exact matrix A. So you basically have the lower triangular matrix and the upper triangular matrix, which results in A right here. Right, that looks pretty good and that looks pretty simple. So what about the case if we have more complex matrix? What if we have, for example, matrix of size 3 by 3? All right, so let's say we have the matrix A, which looks like this, and we need to get LU factorization of that. So to get this, you just have to reduce this matrix again to the upper triangular form. It's pretty simple. Just keep track of the operations that you apply here. We're going to apply two elementary operations. First of all, we're going to take the first row and apply this row, multiply this by -2 and apply it to the second row, multiply this by unity by 1 and apply it to the third row. So we're going to have 0 here, -8, -2, and then 0, 8, and 3. Now we just need to take this second row and apply that to the third row, and we're gonna have 2, 1, 1. So this is what we end up with. This is the upper triangular matrix U. Now we need to keep track of those operations that I already applied and form the matrix L. So overall, we applied 3 elementary operations. So the first thing to keep in mind is that all the elements on the main diagonal are 1s. Upper elements are always 0s because this is lower triangular matrix. And lower elements are the negatives of those exact multipliers that you use to simplify your matrix A and reduce it to the upper triangular form. So you have -2, that means you have to 2. Then you applied 1 as a multiplier, that's you have -1 here. And then you took the second row, multiplied that by 1, and applied it to the third row. That's you have -1 here. You have -1 right here. And so this is your lower triangular matrix. And again, you can make sure this works and this holds by multiplying L and U matrices, finding their product, and making sure this product equals to the original matrix A. And you can see this actually holds. This is the exact original matrix A. So this is the whole point behind the LU decomposition. Now let's try solving the systems of linear equations. But to begin with, I would like to introduce the concept of systems of linear equations. The concept is pretty simple. Let's suppose we have the following systems of linear equations. So we basically have 3 linear equations here, and the system is kind of the bundle of those equations, right? By matrix A, I'm going to designate the matrix of all coefficients in these linear equations. By matrix B, I'm going to designate the constants. That's 5, -2, and 9. There we go. And then we have X. Well, X is kind of the vector X, which consists of X, Y, and Z. And you can see that these systems of linear equations is the exact same thing. Well, it's basically equivalent to this form, to this kind of notation. A matrix multiplied by X gives you the vector of constants. And now there is such thing as augmented matrix. Augmented matrix is the matrix which consists of coefficients of matrix A and the vector of constants of the systems of linear equations, and it looks like this. Now let's try solving this problem using Gaussian elimination. Many of you are already familiar with. First of all, I'm going to use the forward elimination. So I multiplied the first row and applied that to the second and to the third row to get zeros in the first column. Simplifying further, we're gonna get the following augmented matrix, which is the equivalent to the original matrix, and now we can just use backward substitution to get those values. For example, if this is the coefficient before Z, then Z equals 2. If Z equals 2, then -y, -8y minus 2Z equals -12. We know this one is -4, therefore our Y equals 1. Therefore 2x plus Y plus Z equals 5, which means 2x equals 5 minus 1 plus 4. This one gives you 3, 8, which means x equals 4, which is wrong. This is the wrong result. I made a mistake here. That's because that should be -2, and that should be -3, which gives you 2, thus you have 1 in the x. Therefore, your vector x is kind of the solution to this equation, to the system of equations 1, 1, and 2. This is the result. Cool. Now let's try applying LU decomposition to find that. So if you take a careful look here, you know that our LU decomposition, our matrix A, is actually the same matrix for which we already found the LU decomposition. And this is the exact matrix which consists of 2 upper and lower triangular components, 1, 0, 0, 2, 1, 0, -1, -1, and 1, times 2, 1, 1, 0, -8, -2, 0, 0, 1. Here it is. So we know that it consists of L and it consists of U, and your system of linear equations can be simplified to AX equals B, which is the exact same thing as LU x equals b. Now we can substitute ux as y, which means that we have ly equals b. So what is y? Y, again, is this the vector which consists of u1, u2, u3. For simplicity, this is not the exact same thing as u variable, as y variable. This is just the vector y. I probably should have used different notation here to make it clear, but never mind. It's just the vector, right? So all we need to do is just use the fact that our ly equals b. That's we know that x and its coefficient before the x is 1, right? So we know that 1x is equal to this value from b, and this is the 5. We know that b is 5, -2, and 9. So x equals 5. So if x, so not the x actually, y1 in this particular case, equals 5. So if y1 equals 5, therefore 2y1 plus y2 equals -2. It comes from here. Take a look. You have 2 and 1, which equals -2 here, right? On this side. So that will give us y2 equals -2 minus 2y1, which equals to -12. And then applying the same reasoning, you can see that y3 is actually equal to 2. Therefore, our ux equals the following column: -2, -12, and 2. And again, apply the same kind of reasoning for backward substitution now. So now apply the same kind of reasoning here. You know that z and its coefficient 1, this is the exact same coefficient that comes from the upper triangular representation, equals to 2. That's our z equals 2. Therefore, -8y minus -2z equals to not a 2, but what is there again? In our y, it is -12. Thus we have -8y, -4 equals -12, which means our y equals -1. Oh, sorry, 1. And therefore our x, if you calculate the result for the first row here, that would be 1 as well. So this is the exact algorithm for using the LU decomposition for finding the solution to the system of linear equations 1, 1, and 2 as our result, the exact same one as we did for the Gaussian elimination. So that looks pretty weird, right? LU decomposition looks apparently much more tedious and consists of unnecessary extraneous steps. We have to do it, and we need to keep track of an additional matrix, such as a lower triangular matrix. It feels pretty redundant when you need to calculate something by hand. So what is the whole point? Well, it is more convenient to solve the systems of linear equations by hand using Gaussian elimination and relying on Gaussian elimination. It becomes much less desirable when it comes to solving large number of systems of linear equations of large sizes, let's say 1000 by 1000 matrices. If you have a fixed matrix and you need to solve the systems of linear equations to this fixed matrix, but for different vector columns, you need to apply Gaussian elimination every single time when you need to find the result of these systems of equations. In fact, when you apply the Gaussian elimination, you spend roughly n-cube operations to make it work. If you have one large matrix, as I mentioned, for example 1000 by 1000, you will end up having 10 to the power of 9, which is 1 billion of time complexity, which will be a tremendous amount of work if you have, well, let's say 1000 matrices. What about LU decomposition? When you need to compute the LU decomposition, you still spend n-cube operations for it. However, then it just comes down to two main operations, backward and forward substitutions, which is significantly cheaper, a quadratic algorithm, which is only n square of time complexity. So overall, you will only have 1 million operations of time complexity if you had a matrix of size 1000. Alright, so to put it shortly, the core idea is this. You take your original matrix, the one that usually represents a physical system or a set of constraints, like a bridge structure or engineering problem, and you decompose this into two simpler triangular matrices, one lower and one upper. It's a bit like factoring a large number into smaller components, but instead applied to the whole grid of equations instead of a single number. So the entire reason why this matters and what it makes so powerful in scale comes down to computational efficiency of this algorithm. In fields like engineering, physics, computer graphics, you rarely solve a system of equations once. You have one static structure and you need to test it how it responds to different set of constraints, vectors, and to thousands of different external forces or inputs. If you used standard elimination from scratch every time you need to compute that, you will end up having tremendously more work done, because you're repeating the exact same computationally heavy operations over and over again, for no reason whatsoever. By splitting your matrix into two lower and upper triangular matrices, you do the hardest, most expensive work just once. And after this, solving this system of linear equations for each individual vector becomes much simpler. And because your matrices are just triangular, you can handle this using backward and forward substitution as I demonstrated in this video. So what was once a massive and heavy computational bottleneck turns into quick cascading chain of basic algebra, saving an immense amount of work. So that's LU decomposition, not abracadabra at all. You split the matrix once into two components, lower and upper pieces, pay the expensive cost only once, and then every new system is just backward and forward substitutions. And that's the whole trick. I really hope you found this video helpful, and if you did, or if you have any questions, feel free to leave them in the comment section below. Thank you for watching. See you in the next one. Bye.